Hello everyone, welcome you all in my lecture number 5. Most probably this lecture is the maybe last lecture of tau and sigma function. So let's begin. So here is a theorem which says that for every k greater than equals to 2, if 2k minus 1 is prime, then we have to show that n equals to 2k minus 1 in bracket 2 to the power k minus 1 satisfies the equation sigma n equals to 2n. Initially, according to the question, we have 2k minus 1. 2k minus 1, it implies that 2 raised to the power k, which always be a even number, and minus 1 must 2 raised to k is must be a even number, and 2 raised to k minus 1 always universally satisfies the property that it will be the odd number. So now they according to the question, they provided us that 2 raised to the k minus 1 is a prime. Then we can include another thing, that 2 raised to the power k minus 1 must be not equals to 2. That 2k minus 1 odd number, that means it must be a odd prime. So now we have that n equals to 2 raised to the power k minus 1 dot p. So according to us, now sigma n equals to sigma of 2 raised to the power k minus 1 dot p. Now, as we know that sigma is an multiplicative function, that we can write it in the form of 2 raised to the power k minus 1 dot sigma of p. That means the power of 2 raised to the power k minus 1 of sigma is must be nothing but, it may be 2 raised to the power k minus 1, and the sigma of p is always p plus 1. Here we can write that sigma is a multiplicative function, and we have that sigma of p raised to the power alpha equal to p raised to the power alpha plus 1 minus 1 by p minus 1. That means we can write it as the 2 raised to the power k minus 1, and we can write p as 2 raised to the power k minus 1, as according to the question that it is given that 2 raised to the power k minus 1 is a prime number, and plus 1, which says that it is I am writing here 2 raised to the power k, and in bracket 2 raised to the power k minus 1. That means 2 into 2 raised to the power k minus 1 into 2 to the power k minus 1, which is nothing but our 2n, which satisfies our question and hence proved. So in our next question, we have, if n and n plus 2 are pair of twin primes, then establish that sigma of n plus 2 equals to sigma of n plus 2. So initially we have to know that what is twin prime. So what is twin prime? Two numbers are said to be twin primes. For an example, that if we consider an example which is 3 and 5 are twin primes. So if we write it as sigma of n plus 2, we have, that means sigma of n plus 2 equals to n plus 2, and it has another factor 1, that means n plus 3, and another sigma of n plus 2 equals to n plus 1 plus 2, that means n plus 3, as both are equal. Therefore we can say that since p is a prime, number, then we have sigma of p must be p plus 1 from our past lectures remark. Therefore sigma of p equals to p plus 1, and in this case we have n and n plus 2 are co-primes. Here n and n plus 2 are co-primes. If we move to our next example, it says that for a given integer k greater than 1, that means k must be greater than 1, so we have to show that there are infinitely many integer n for which tau of n equals to k, and there are finitely many integer n for which sigma of n equals to k. So initially I am taking our first question, that is there are infinitely many integer n for which tau of n equals to k. So what is the k? K is nothing but k must be greater than 1 for any prime p and for n equals to p raised to the power k minus 1 we are taking. That means in this case our tau of n equals to k minus 1 plus 1, which is nothing but our k itself. Since number of primes is infinite, because there are infinitely many primes in our number system, number of integers n is also infinite, and hence we can say that there are infinitely many integers for which tau of n equals to k. So it is our first proof. So in our next question, next part of the question, they ask that there are finitely many integer n for which sigma of n equals to k. So similarly in this case also we will start our theorem by saying that since for any n greater than 1, here we are taking n n greater than 1 has at least two divisors, 1 and n. Obviously we know that for any number there exist at least two divisors itself. For any number that if we log into the divisors of that number, then we will find one and that number in the divisors list of that number, though it is a prime number, though it is a composite number, or though it is any positive integer. So we can write it as in the form of sigma of n greater than equals to 1 plus n, which implies sigma of n equals to k, because 1 plus n it is a fixed integer as per our question, that we can write it in the form k greater than equals to 1 plus n. That means k minus 1 greater than equals to n, which also implies n must be lesser than equals to k minus 1. Here k is the fixed, there are only finitely many n's, at most k minus 1 integer n. Therefore for any finitely many n's, at most k minus 1 integer n, the value of sigma of n is must be nothing but k, which concludes our proof. So if we move our next question, here they asked that for any integer, positive integer, we have to show that the sum of the sigma of d equals to sum of n by d tau d. D is the divisors, that's again. So initially we have it is given that f we are taking that f of n equals to this side, and this side equals to g of n. So if we take initially we take that f of n and g of n, which means m and n they always must be a natural number, and GCD of m and n are 1. So in this case, in the first initial place, we'll try to prove that f of n and g of n are multiplicative. So as per the definition of multiplicative, what is known by the multiplicative, that if there are two integers m and n belongs to natural number, and the GCD of m and n must be a 1, and it must be satisfies the property f of mn equals to f of m dot f of n. So we have to show in the case of f of n in the form of multiplicative identity, that is sigma of d divides mn by d tau of d. So we know that we can write d as the product of d1 dot d2. So here we are doing this, where d1, our d1 divides m and d2 divides n. So if we write it in the form of mn by d1 dot d2, product of d1 and d2, divisors of d, that means tau of d1 dot d2, which implies if we take the d1 portion and d2 portion partially, then we have that m by d1 and n by d2. So that means our this number, that this part is known as f of m, and this part can be represented as the f of n. So initially we take f of mn, and currently we, after calculation, we get f of m dot f of n, which is a multiplicative function. So in our next case, we will show that g of n is multiplicative. So here it follows that g of mn, we start by g of mn, that means here it is given at sigma of d. So as earlier we did that, we wrote that d equals to d1 dot d2, and here d1 divides m and d2 divides n. So d1 divides m and d2 divides n, that means sigma of d1 dot d2, since sigma is also a multiplicative function, that means sigma of d1 and sigma of d2, if we take it this part, then this as it is that g1 d1 part, we can write it in the form of g of m, and that is d2 part, and divides by n, it will be n, then it can be written in the form of g of n. So we also, there means g also can represent in the form of multiplicative function. So we have that f and g are both are multiplicative function. So if we look into the question, that here it asks that us for any positive integers n, show that this f of this side equals to this side. So initially we showed that f of n and g of n are multiplicative. That means sigma summation sigma of d and summation n by d tau of d are both are multiplicative function. Now we'll write it in the form of p raised to the power alpha. Why we write this in the form of p raised to alpha? Because in our previous lecture we learned that therefore is for any square of integer we can represent that by the p raised to alpha. So we are replacing n by p raised to the power alpha, and we have p raised to the power alpha by d tau of d, and if we broke the summation, then we have p raised to the power alpha tau of 1 by p of by d equals to 1, and p raised to the here d equals to, for the d equals to 1 this happens, for d equals to 2 this happens, for d equals to, similarly it's so on. That means p to the power alpha by p, and here it will be tau of p, and similarly for d equals to 1 it is, and similarly p raised to the power alpha by p square and tau of p square. For actually it is happening for p raised to the power for p raised to the power 0, p raised to the power 1, p raised to the power 2, and so on, p raised to the power alpha. So here we have p raised to the power alpha tau, and we all know that tau of 1 is always 1, and we can write tau of p can be write in the form of 2, because tau of p is nothing but the number of divisors of a prime, and from our first lecture remark we know that the number of divisors of prime are always 2. That means tau of p can be written in the form of 2, and here we have p raised to the power alpha minus 1, and similarly so on. We have 3 raised to the power p alpha minus 2 and alpha plus 1 at last. So if we focus on g raised to the power gp of alpha, similarly we have sigma of 1, sigma of p, sigma of p square. For p equals to 0 we have sigma of 1, for p equals to p equals to 0, p equals to 1, so on. So here for p equals to 0 we have sigma of 1, for p equals to 1 we have sigma of p, and for p of p square we have sigma of p square, and so on. We have sigma of p raised to the power alpha. So we know that for sigma of 1 are always 1, and sigma of p are always nothing but our p plus 1, because the sum of the divisors of a prime are always p plus 1. That means sigma of p is p plus 1, and sigma of p square. So how many divisors p square have? So p square have 1 as a divisor of p square, p itself a divisor of p square, and p square is another which is the divisor of p square. So for sigma of p square we can write 1 plus p square. So here we wrote this, and similarly for sigma of p raised to the power alpha we can write it in the form of 1 plus p square, and so on, followed by p raised to the power alpha. So here we can write, here 1 repeats how many times? For 1, 2, 3, that means for alpha plus 1 times 1 repeats, and for 1 plus p square, 1 plus p square, and so on, 1 plus p square, it repeats for alpha times. That means here we wrote that p repeats alpha times, alpha p, in every case that we have p, and so on. For p raised to the power alpha it repeats only 1 times, that means p raised to the power alpha into 1, and before this we have p raised to the power alpha minus 1, because just last function before this it will be to p raised to the power alpha minus 1, and p raised to the power the sigma value of p raised to the power alpha plus 1, and the number of having p raised to the power alpha 1 will be 2. That means p raised to the power alpha minus 1 into 2. So now we can, if we look into our first part which is f of p of alpha, and if we now look into our second part which is g of p of alpha, both are quite similar to each other, and in fact similar. That means that means by our known result, that known result of multiplicative function, that if f of p of alpha and g of p of alpha for any alpha belongs to I am writing this in here. That means for any f of p of alpha and g of p of alpha, for all alpha belongs to n union 0, natural number including 0, then f of n equals to g of n for all n. That means here f of n and g of n are multiplicative. We also showed that. That means we can write it in the form f of n equals to g of n for all n, and our question is here, it is proved. So I am concluding this lecture number 5 here, and it may be the last lecture of this series of tau function and sigma function, but I will extend this lecture to lecture number 6. There will be the lecture number 6 will be the extension of lecture number 5. There will be a single question, single theorem, which will be this similarly to this whatever we proved now. Okay, let's meet in the lecture number 6.